Okay. Good evening, everyone. Welcome to this live session. Uh, Live on 23 3 2026, so 5 p.m. So, this week, what we do is we'll see the week 6 content. So, week 6 basically on two topics. So, one is on the RH criteria, and another is on root locus. Okay, so this week, so what we will do is we will cover this RH criteria and problems today. We'll cover RH criteria and problems, and on Wednesday we'll cover the problems on the root locus. Okay, so basically, what is this route Harvich criteria? So if you see the, I'll roughly go through the content review. If you are having any doubts, you can ask me. Then we will solve the problems. Okay. So this is the T of S. Generally, we have this transfer function, numerator over denominator. Okay. So basically, what we call, so if you take this Q of S equal to 0, we call that is as the characteristic equation. Okay. So in closed loop setting, so if you see this one, if you have a controller K of S and a plant G of S, if you find the transfer function, so the transfer function is this one, Y of S by R of S, output by input. So that will be of this expression, correct? Any queries here in this? Hope this is clear. Okay, so this is for a basic closed loop transfer function. Okay, so in this, if you take the denominator, that is nothing but this one, 1 plus GKH. Okay, where H is the feedback, K is the controller Laplace transform. Okay, so 1 plus GKH equal to 0, denominator of this function. Okay, that we call it is as the characteristic equation. Okay, so to that characteristic equation we could write in this form. Okay, and find that P1, P2, etc., Pn are the poles. Am I correct? So P1, P2, etc., Pn, so they are nothing but the poles. Correct. So am I audible?
Yes, sir, audible.
Yeah. So these are the poles of the transfer function. Once we have the poles, okay, so we will check the poles location. Either they are on the, all the poles are on the left side, or some poles are on the right side. Based upon that, we will decide whether the system is stable or not. That we have seen already in the week 3 or week 4. Okay, so now in continuation to this, so this RH criteria, suppose when you have this Q of S, okay, so this characteristic polynomial, if this Q of S is of order, let's say order is 2, okay, so we can easily find, if order is 3, we can easily find the roots. What if the order is greater than or equal to 4? Can we find these, the P1, P2, etc., Pn, the which are the roots of this Q of S equal to 0 easily? We cannot find, correct? Manually, it is not easy to find. Yes or no?
Yes, sir.
Yeah. So in that case, this RH criteria would help us to decide the stability of the system without actually finding the uh, roots of this characteristic equation. That is the basic motto of this RH criteria. When you have the order of this, the Q of S characteristic polynomial is greater than or equal to 4, where we find it is difficult to find the roots manually. Okay. So now this is the procedure. What we do is static. So this Q of S we could write in this way, where we have these AN are the coefficients. in the same equation. So let's say we could write in this way. So if you factor it out, okay. So this way, if you expand it, okay. Now, if you observe here, okay. So to make sure that all the poles are exist, all these the poles are all these roots are existing on this left hand side, okay. So the conditions would be as follows, okay. All these coefficients, okay. So they must be non-negative, or they must have the same sign, either all positive or all negative. Okay, so that must be the condition. If we wanted to say that all poles must exist in the all roots must exist in the left hand side of the j omega axis. Okay, that is a requirement for the stability a stable system. Okay, so let us say here, if you take these ratios, an minus 1 by an minus 2 by an. So simply if you are taking this an out, okay. So here we said that all ratios must be non-negative. Suppose if you see here, as I said, all ratios must be non-negative, either they are all positive or all negative. Okay, that should be the condition. Suppose if you see this polynomial, so here all coefficients are what? All coefficients are positive. Yes or no? All coefficients are positive. But if you see these roots, you can see these roots. So for this equation, what are the roots? S is equal to minus 2, S is equal to 0.5 plus or minus J 1.936. So if you see them here, so minus 2 here, okay. So the minus 2 pole is here. So the other two poles are here, okay. So now whether the system is stable or not, system is unstable, correct?
Yes, sir. Unstable.
Because two poles are on the right hand side. But here, having these all coefficients non-negative, so it means that it is not the sufficient condition. It is necessary condition. Even if all these coefficients are positive here, so there is a possibility that system would become unstable. Okay. But if any of these coefficients are negative, system becomes automatically unstable. Okay. But the system becomes stable. The necessary condition is they must be non-negative. I hope this is clear. Okay. So now let us start this RH criteria. So in RH criteria, what we do is first condition is necessary condition. All those coefficients so must be positive. Okay. Then we will find the necessary, sorry, that is necessary condition. Then we will find the sufficient condition. Okay. Is this clear? So if a characteristic polynomial Q of S is equal to 0 is given, this would have the coefficients. The first condition is all coefficients must be positive. Then second condition is we'll find that sufficient condition. So it has two steps. So this RH criteria. So in RH criteria, what we do is, so this is our characteristic polynomial. Okay. So the first condition is all those coefficients must be positive. Then second, what we do is we will form this RH table. We will form this RH table. So now here you could see, I'll erase this one here. Okay, now you could see this one. I'll erase this one also. Okay, so I'm writing here the coefficients S minus N, S minus N minus 1, S minus N minus 2, etc. S for 0. This is how we first form the table. First, we'll write all the powers of S. Then we'll write here AN. The next coefficient goes here, AN minus 1. The next coefficient goes here. Next coefficient goes here. So next coefficient goes here. Okay, next coefficient goes here, etc. Is this clear?
Yes, sir. Clear.
Okay. So first we will put all those coefficients in first two rows. Okay. Then we will find these using a method. Okay, so that means we will find all these bn minus 1, bn minus 2, bn minus 3, cn minus 1, cn minus 2, cn minus 3. That is called as finding RH array. Okay, so using these first two rows, we will find the rest of the rows. Okay, so let us see this. So here, as I said, first two rows are fixed. They come from the characteristic polynomial. Okay, next, you can see this bn minus 1. How do we find? You can see this bn minus 1. So bn minus 1, what we do is, so we will multiply this an minus 1 with an minus 2, you could see, minus this term. Okay, then an with an minus 3. Divide by this an minus 1. Can you see these arrows? That is how we will find bn minus 1. Okay. Next, bn minus 2, this term. What we do? We will multiply an minus 1 with an minus 4 and the an with an minus 5. So this one minus this one. Divide by again with the same an minus 1. So that is bn minus 2, bn minus 1. Similarly, we will find bn minus 3. Bn minus 3, how do we find? So this one with the next term, this one with the next term, again divide by an minus 1. Is this clear? Any doubt? Any doubt? Okay,
So
so
how
that
do
is
we know that with what we have to divide that?
divide by an minus 1 only for every term, first term only.
Okay, sir.
Okay, yeah. So next we will get cn minus 1 here. Okay, so cn minus 1, for finding cn minus 1, what we do? We will use these two rows. So cn minus 1 will be like, so this term multiplied this minus this term multiplied by this divided by bn minus 1. Is this clear? So to find this row, we will just use the above two rows. So cn minus 2, how do we find? This term multiplied by this term multiplied by this divided by bn minus 1. Is this clear?
Yes, sir.
Any queries? Okay. So here you can see that. So cn minus 1, cn minus 2. So these two. The green ones are cn minus 1. So this one, divided by bn minus 1. So the red ones, this one, divided by bn minus 1. That is cn minus 2. Hope this is clear. Okay, so that is again you will find cn minus 3. Next, if you are getting the dn minus 1, so you will just use these two rows. Okay, so once you fill up everything, what you do is, this we call it is as the RH array or RH table. Okay, so then what we do is we will observe only the first column. We'll observe only the first column. We will check from term to term. We'll check between these two terms whether they both are positive or negatives. Then we'll check these two terms whether they both are positive or negative. We'll check these two terms. We'll check both are positive or negative, right? So to become stable, every sign has to be same. Every sign has to be same. If there is any sign change, we would say that system is unstable. Okay, number of sign changes will be equal to number of the poles staying on the RHS side. Okay, so this is RHS, this is LHS. Is this clear? Okay, so here you could see. Okay, so once you fill this table, we call this is the RH table. Then we will, for every two rows, we will check, is there any sign change or not? Every two rows. Okay, if there is no sign change at all, no sign change means all the terms either positive or all the terms either negative. Okay, then we say that system is stable. If there are any sign changes, we say system is unstable, and number of sign changes is equal to the number of poles on the RHS side. System still unstable, but how many poles are there on the RHS side? So that will be decided by the number of sign changes. Is it clear? So that is how we will decide. Here we don't need to calculate the roots of the characteristic polynomial. Okay. Suppose if you see this one, I'll quickly do this example. So now here we have S cube is the highest. S cube, S square, S, S power 0. Okay. So what is S cube coefficient? That is 1. Next we have S square. That is 4. Next what we do is we have S coefficient. We don't fill that S coefficient here. Okay. So we will fill that S coefficient alternatively, 9. Okay. Next we have S4 0 coefficient is 10. We don't fill that one here. Okay. Instead we fill that one in the second row only. Is this clear? Okay. It means that all the coefficients will be fitted in the first 2 rows itself. Now, so how do we find this? So we find that, so 4 multiplied 9 minus 1 multiplied 10 by 4. Okay, so this is the we do. 4 multiplied 9 minus 1 multiplied 10 by 4. How much it is? 36 minus 10. How much it is? 26 by 4. Correct? 26 by 4. Okay. Next, we don't have anything. So this will be 0. So next again, if you do the same thing, so 26 by 4 multiplied by 10 minus 4 multiplied by 0 divided by 26 by 4. How much it is? It will be 10 only. Correct? It will be 10 only. Now you could see this first row only. First row. Okay. So is there any sign change from here to here? No, both are positive. Is there any sign change from here to here? No, both are positive. Is there any sign change from here to here? No, both are positive. Okay. Then you will see no sign changes and system is stable. Is this clear? Okay. Even if you find the roots also, okay. So you will get all roots will be negative real parts only. That means what? All roots will be on this side only. Is this clear? Any doubts? Any queries?
No, sir.
Yeah. So this is how you will proceed. Yeah, you will see these roots. I'm sorry. You can see these roots. So the roots are at -2 is one root. Another root is at -1. So this is -1 plus or minus J2. So this is plus J2. This is minus J2. So these are the 2 poles. Can you see that?
Sir, how did you got
So
that roots?
no, this one directly if you manually calculate it. Okay, so 2 methods, manually calculate and RH criteria. Okay, RH criteria
So
is,
using RS criteria, how can I find the roots only?
no, we are not finding roots by using RH criteria. This is RH criteria. RH criteria, what we are doing? So we keep S cube, S square, S power 0. Okay, so S cube coefficient is 1. Then S square coefficient is 4. Then S coefficient is 9. Then S power 0 coefficient is this. So we fill the first 2 rows. Is this clear? Then other rows, we
Yes,
will
sir.
use this multiplication rule. Once we have this table, we will only check the first column. Okay, in first column, if you see from first element to the second element, is there any sign change? No, both are positive, correct? Then here to here, any sign change? No, both are positive. Here to here, any sign change? No, both are positive. Hence, the system is stable. Clear? So without finding roots, I could be able to decide that system is stable or not. Now to check manually for this, these are the roots. Okay. Now we are verifying through roots. How, where the roots are existed in LHS only.
in the LHS.
Yeah, that's how we are proving it. That's how you can verify it. Okay. So the RH criteria having its advantages when these uh, polynomial order is more than 4, 5, etc. We cannot find the roots manually. Yes or no? Until unless we use computers to calculate the roots. But simply by forming this table, we can find the roots. Am I correct? Yes or no? Any queries here? Any queries? Any doubts?
Excuse me, sir.
Yes.
Suppose for in finding RH
Ah,
array, if in the power of S3, S2, S and S0, if
ah.
there is a sign change between 1 to 4, in one this is one sign change
Yeah,
from
yeah. If there
positive
is a
to,
sign change, okay.
and in
Ah,
also then S to from going S to S0 there will be also a sign change. Then what can you say about the stability?
yeah. If there is any sign change, directly we say that system is unstable.
Whether it has a one time sign change or two times, it if
Yes, yes,
there
yes.
is a sign change, we can
If there
directly
is a
say
sign
that
change,
system is
we could
unstable.
say that system is unstable. Sign change,
Okay.
okay. And number of sign changes indicates the number of roots on the LHS, RHS side.
Okay. Okay,
Okay.
got it.
If there are no sign changes, system is simply stable. So it means that to become stable, either all has to be positive here or all has to be negative. Clear?
Sir,
Okay.
can you do an example of a unstable system?
Unstable also we can do. So just give me a minute. Okay. So we'll discuss roughly this, then we'll go ahead. Okay. I'll do for unstable also. Okay. You can easily see. Otherwise, let me do an example. You'll understand it. Can you see these notes?
Yes,
Okay.
sir.
Let me, yeah.
Yes,
So
sir.
let me do some example. Okay. Suppose I have a feedback system. Okay. So feedback, I have open loop transfer function as g of s. Okay. And I have, let's say this is plus minus, this is r of s, this is y of s. Let's say we have h of s. This is closed loop system. Am I correct? Okay. So
Yes, sir.
here, what is y of s by g of s? Y of s by r of s? Can anyone tell me? If you do that, you will get like this: g of s, h of s by 1 plus g of s, h of s. Am I correct?
Yes, sir. Correct.
Yes. So let us take here h of s is equal to 1. So what is it? Y of s by r of s equal to what? G of s by 1 plus g of s. Correct? Okay. So now let's say I'm giving g of s as k by s plus 1 divided by s into s minus 1 s plus 6. Okay. So basically, what is this one? This g of s is nothing but what? Open
Open
loop
loop.
transfer
Yeah.
function.
Yes.
Correct? What is my
Yes.
closed loop transfer function? This one, y of s by r of s. Correct? What is it basically? So that is nothing but this expression, correct? Divided by 1 plus, I'm sorry, divided by 1 plus same expression. Am I correct? So k into s plus 1 by s into s minus 1 s plus 6. Am I correct?
Yes, sir.
Right? So how that expression will change to? So I can simplify that one to k into s plus 1 by s into s minus 1 s plus 6 plus k into s plus 1. Is this correct? Both denominators gets cancelled. Correct?
Yes,
Yes or
sir.
no?
Correct.
Right?
Yes,
So
yes.
what is my characteristic equation now? Tell me. Characteristic equation is nothing but s into s
Yes, sir.
minus 1 s plus 6 plus k into s plus 1 equal to 0. Yes or no?
Yes, sir.
Okay. So now basically k here, uh, I can write it like this one as something like I can put my k here, correct? I can say that this is G1. Can I say that? So where G1 is nothing but s plus 1 by s into s minus 1 s plus 6. Am I correct? And this is G2. G2 is nothing but k. What is basically G of s is nothing but G1, G2. Am I correct? Yes or no?
Yes, sir.
Yeah. So this is my characteristic equation. Now my question is, so if we see our previous week material, here K is nothing but what? Proportional controller, correct? Okay. Now my
Yes.
question is, what is the value of K, okay, or range of K, okay? Range of K, the system is stable. Can I ask that question? For what range of K, the system becomes stable, correct? Yes, sir. Is K, suppose if I substitute K is equal to 10, okay, will this will have all the poles on the left hand side? We are not sure, correct? If K is equal to 100, if all the poles will be on the left hand side, we are not sure, okay? Now we have to fix the range for K in such a way that all the poles will be on the left hand side, correct? Okay, so is this question clear? we
Yes,
wanted
sir.
to we wanted to fix the controller gain K in such a way that if I find the poles of this closed loop transfer function, that transfer function should have all the poles on the left hand side. That is our requirement. I need to find that range of K. Okay. Now let me consider this characteristic equation again. So what is the characteristic equation? So s multiplied s minus 1 s plus 6 plus k multiplied s plus 1 equal to 0. Okay. So if you simplify this, okay, so you'll be getting something like this: s cube plus 5s square plus k minus 6 s plus k. So please verify it later. Okay. This is our equation, correct? Now I wanted to apply this RH criteria to find the range for k. Okay. So what is the RH criteria? First step, write down these s powers. S cube is highest, s square, s power 1, s power 0. Is this clear?
Yes, sir. Clear.
Okay. So now tell me these terms. So first s cube coefficient is 1.
One.
Okay. Next coefficient, s square coefficient is 5. Okay. Next s coefficient is k minus 6. Okay. We write alternatively. Next s power 0 coefficient is k. Is this clear, everyone? Always we fill the first two rows only, alternatively. Is this clear? Any doubt? Any doubt? Okay. So now how do I find this? So I multiply k 5 with this term, 1 with this term, divide by 5. Yes or no?
Yes, sir.
Okay. So what is that? 5 multiplied k minus 6 minus k, that is nothing but 1 multiplied by k, 5 by 5. Is this clear?
Yes,
Okay.
sir. Clear.
Since there are no terms here, I can put this as 0. Okay. Next, how do I find this term? So what I do, I multiply this term with this, 5 with 0, divide by this whole term. Am I correct? Can you tell me what is this term is?
Sir, K.
That will be k. Why? Because you are multiplying this term with k minus 0 divided by this term. That will be k. Now, what is the condition for stability?
All column signs are same.
All all these first
First
column
column.
elements should be same. Okay, already you know that this 1 and 5, they have positive signs. Okay, so same sign means this term and this term also has to be positive only. Correct? So positive means what is the first? Let's say this term is, last term is k is greater than 0. Correct? Yes or no?
Yes, sir.
Okay. What is the other term we have? 5 multiplied k minus 6 minus k by 5 is greater than 0. Okay. What is it? Can you write it here? 5k minus 30 minus k is greater than 0. Correct? So 4k minus 30 is greater than 0. K is what? 4k is greater than 30. K is greater than 30 by 4. How much? So that is 7.5. Correct? So now we have two things. Okay. So you have two terms. K is greater than 0. K is greater than 7.4, 7.5. Okay. So this is 0. This is 7.5. Okay. So one is K is greater than 0. All this one. Correct. Another is K is greater than 7.5. What is the intersection? What is the intersection?
After 7.5.
After
Yes,
7.5.
this term. Okay. So combining both is, that is your k is greater than 7.5. So if you substitute k is greater than 7.5, any value, okay, in this column, you will get what? You will get the positive value. You will get this also positive, this also positive. Am I correct? Yes
Yes,
or
sir.
no?
Correct.
If you
Yes, sir.
take
Correct.
any value less than 7.5, sometimes, okay, this may be positive, but this may not be positive. Okay, if this is not positive, if this is negative, what will happen?
The system will unstable.
System becomes unstable. Why? Because sign change is coming into picture. Clear? So now finally, for the system to be stable, my k has to be greater than 7.5. Okay. Any query in this? Sorry. Any query in this example? So this is the example of using the RH criteria for tuning the controller. Okay, it is not like you will be choosing randomly the k value. You wanted to choose the k value for the system to be stable. Is it clear? Any doubt? Any doubt?
No, sir.
If you're having any doubt, please ask me. Okay, so yeah, next. So here what we are trying to doing here, if you see, so to find how do we get 26 by 4? We are multiplying 4 multiplied 9 minus 1 multiplied by 10 divided by 4, correct? Right? Suppose in some cases, what if you get 0 here? What if you get 0, what will happen? While finding this term, you will multiply this, you'll multiply this and divide by what?
0 divided by. Then
So
it
that
will
is
undo.
undefined, correct? This we call it is as a special case 1. This we call it is as a special case 1. Right? Now question is how to handle this. Okay. So now here you can check this. So to handle this, what we generally do is, so this is where we are getting 0. Okay, this is where we are getting 0. So that 0 we will replace with epsilon. Epsilon means a small number epsilon. Then we will continue the calculations using that epsilon. Okay. Then what we do is, okay. Then what we do is, so we will take these terms, limit epsilon tending to 0. For example, here you could see this. Can you tell me what is this characteristic equation here by observing this? What is the characteristic equation? S power 5 plus S power 4 plus 2S cube plus 2S square plus 3S plus 15. Am I correct?
Yes, sir, correct.
Yeah. So now we are simply writing S power 4, S power 5, S power 4, S cube, S square, S power 1. So 1 here, then next coefficient 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 here. Clear? Any query in this? That is how we are forming the first 2 rows. Okay. Next, this term. This term. Okay. So this term basically, how do we find? This 1 multiplied by 1 multiplied by 2, 1 multiplied by 2. Okay. So divide by 1. Okay. You'll get in fact 0 here. Why? Because 1 multiplied by 2 is 2. 1 multiplied by 2 is 2. So it will become 0. 0 by 1 is 0. So you're getting 0 here. Okay. Then 1 multiplied by 3. Then this 1 multiplied by 15. So 3 minus 15 minus 12 divided by 1. How much it is? Minus 12. Is this clear? S cube row. Any doubt? S cube
No,
row,
sir.
any doubt? Yeah.
No, sir.
So now if you continue with this 0, what will happen? So 0 multiplied by 2, 1 multiplied by minus 12, divided by 0 you have to take. That is undefined. So that's why what we do, this we consider it is as a special case and replace that 0 with this epsilon and continue the calculations. Now if you continue the calculations, what will happen? Instead of 0, you're continuing epsilon. So epsilon multiplied by 2, 2 epsilon, 1 multiplied minus 12, so plus 12, divided by epsilon. Is this clear? Any doubt? How we got this now? Okay.
Yes, sir, okay.
Yeah. So similarly, the next terms also, we will continue the same thing. Now to check the, finally, after getting this first row. Okay. So after getting this first row, what we do? So we wanted to check the sign changes in the first column. What we do is, so we take the limiting for all these terms. Okay. So if you take limit epsilon tending to 0, 2 epsilon plus 12 epsilon. What is this value is? Can you tell me? So if you take that epsilon out, what you get? So 2 plus 12 by epsilon, correct? Yes or no? This is limit epsilon tending to 0. Am I correct?
Yes, sir.
Yeah. So that will be positive value. Okay. So positive value only. And here you have already negative. Remaining all are positive. Okay. So that's why you could see from here to here positive, no sign change. From here to here positive, no sign change because epsilon is small positive value. Okay. From here to here also positive. Then here to here is negative. Why? Because we have this negative sign. Then again, here to here is negative to positive. So this is, there are two sign changes. Am I correct? So hence system is what? Unstable. Unstable, and there are two roots on RHS side. Is it clear? Unstable with two roots on the RHS side. Why? Because we have two sign changes. So from this to this, and then this to this. Is it clear? Any query? Any queries here? So special case one, what it says basically, so whenever you are doing calculations in the first column, whenever you get this 0, replace that 0 with epsilon, continue the calculations. After that, take every term epsilon tending to 0. Then check its sign. You don't need to calculate its value, whether you are leading to positive or negative. Okay, here this is leading to positive sign, positive value. Is it clear? Is it clear? Any doubt? Okay, so that is special case one. Any queries in this? Any query?
No, sir.
Yeah, that is special case one. Special case two is, now consider this equation. Okay, now I am trying to forming the uh, I'm trying to forming this RH table. Okay, so now you can see that the highest order is s cube, s square. So s power 1, s power 0. Okay, this will be 1, then next 5, then next 6, then next 30. Okay, so you can see this 5 multiplied by 6, 30, 1 multiplied by 30, that will be 0. Okay, next, so here you have automatically a 0 because there are no other terms. Now you could see that this entire row becomes zeros. If entire row becomes zeros, what is going to be this next number? Okay, 0 multiplied 30 is 0. 5 multiplied 0 is 0. Divide by 0. 0 by 0 is again undefined. Correct? Okay. So that is because uh, you have this entire row is zeros. Is it clear? Entire row is zeros. In this case, what we do is we will form something called as the auxiliary polynomial. Auxiliary polynomial is something, whatever the zeros you have, just check the row above those zeros. What do you have? 5, 30. What is the maximum power? S square. So we write like this. 5s square plus, is it going to be 30s or 30? It's going to be 30 only. Why 30? Because these are even powers. These are odd powers. Clear? This row will have, this is coefficient of s cube. This is the coefficient of s only. This is the coefficient of s square. Then this is the coefficient of s power 0. Is it clear? So
So
then
here we
we,
have to take only the even coefficients, right?
No, not like that. So this is the row where you have zeros. Take the just above row. If this row is s cube, you have to take s cube and 30s. Okay, that you have to check. Okay, so now you have this auxiliary equation a of s. Take the derivative of this with respect to s. So what is this value? 10s, correct? 10s plus 0. Am I correct? So now replace that 0, 0 row with 10, 0. So this will be 10, this will be 0. Is it clear? Now we have new numbers. Okay, then you can continue the calculations. You can continue the calculations. 10 multiplied 30. This is nothing but 10 multiplied 30 minus 5 multiplied 0 divided by 10. This will be 0. Is it clear? This is nothing but 30. Am I clear?
Yes, sir. Clear.
So that is how you will proceed. Okay. So then again, you have to check the this thing again. First column. Okay. So you can see this example here. So we are getting 10, 0, and final one is 30. Okay. So here, after that, what you have to do is, so check this one. So whether you have sign changes or not, automatically when you don't when you have sign changes, system is automatically unstable. Okay, so again you have to check this, the roots of the characteristic polynomial, sorry, auxiliary equation. So the auxiliary equation says that, okay, so you're getting, if you take this is equal to 0, okay, you're getting s square is equal to -6, s is equal to plus or minus j6. Okay, so you're getting two roots, plus j6 here, minus j6 here. Okay, and system becomes marginally stable. Okay, system is marginally stable, not just stable. Okay, so along with this RH table, you also need to check the roots of the auxiliary equation in this case. Is it clear? Okay, these are the special case 1 and special case 2. Any queries? Any queries? So let me solve an example. This is basically the RH criteria methodology. Okay, let me solve an example. One more example. Mm, okay, let me take this. So let's take characteristic polynomial is s power 4 to s power, sorry, s power 5. So 2s power 4 plus 24s cube plus 48s square plus 25s plus 50 equal to 0. Okay. So now tell me s power 5, s power 4, s cube, s square, s power 1, s power 0. Correct? So what are the values? 1, 2, 24, 48, 25, 50. Am I correct?
Yes, sir. Correct.
Okay.
You are.
So now you could see that you'll get 0 here. Why? Because 2 multiplied 24 is 48, 1 multiplied 48 is 0. Correct? Then next, this is how you will proceed. Am I correct? Then
Yes, sir.
the next one is this way. Again, that is also 0. Correct? 2 multiplied 25 is 50. 1 multiplied 50 is 50. Okay. This automatically 0. Why? Because you don't have these terms. Okay. Now you are getting the entire row zeros. You're getting entire row zeros. In this case, what we do? So we consider auxiliary polynomial. Okay. What is that auxiliary polynomial? So this is the row. You have all zeros. Correct? So consider the row just exactly above. What is that row? 24850. Okay. So now can you tell me the polynomial?
So
So
2s to the power 4,
2s for 4 plus
48 x is s square
s square
48 square,
plus
plus 50.
50.
Okay. Now what is
50.
the derivative of that? So that will be 8 s cube plus 96. Yes. Correct. So we
Yes, sir.
replace this one with 8, this one with 96, and this one is 0 because this is 0. Okay. Now if you continue the calculations, okay. So 8 multiplied 48 minus 2 multiplied 96. Okay. By 8. So you will get some 24 here. So 50 here, 0 here. And again, you can 24 multiplied 96 minus 8 multiplied 50 divided by 24. You will get 79.23. This is 0. And here you will get 50. Okay. So now what it says, so there are no sign changes, correct? There are no sign changes. System is stable. Okay. But check this one, the auxiliary equation. Okay. So 2s power 4 plus 48 s square plus 50. So check the roots. Okay. So you will get 4 roots. You will get 4 roots. So you will get 4 roots. In this case, they are, I think, complex conjugate, or they'll get roots as the j omega axis. Okay. On the j omega axis, you'll get. Okay. Hence, the system is marginally stable. Okay. So here, if you get any sign changes, directly you would say that the system is unstable. Is this clear?
Answer, if we
Yeah.
find the roots of the auxiliary equation, and
Uh,
if how the equation becomes stable instead of marginally stable, what are the criteria for the roots?
oh, sorry. What is it?
Means if we have to find the roots of this auxiliary equation, we get
Yes.
four roots here, and I am
Yes.
getting the roots is plus minus 1 and plus minus 25i. Okay,
Okay.
then
You're getting roots as
plus minus 1 and plus minus 25i.
plus minus J1,
Yeah, plus
plus
minus
minus
j
J
minus 1, j1, and plus minus
25.
25j.
Yeah. So these are
Yeah.
these are the roots on this J omega axis.
So my question is,
Yes.
instead of this marginally stable, the
Mm.
can the system becomes pure stable?
So in that case, you have to push these you have to push these poles to the left.
Okay, in the left, in the LHS, right?
Yes. Yes.
Okay, got
That
it.
is what your controller will do. Generally, when the system becomes marginally stable or unstable,
Yeah.
so you design your controller to push them to the left side.
So
Okay,
changing
means
the value of
like
k.
Yeah, changing the value of
like
k.
Yes, sir.
So
like integral controller
in
you said that.
complex way, changing the values of kp, ki, kds.
Yes, sir.
Yeah, that's what your controllers does. Okay. So this RH criteria is mostly highly useful in case of deciding the stability of the systems without finding the roots. Here we haven't find the roots anywhere. Simply we are forming this RH table, and just by looking at the first column, we are deciding system is stable or not. Okay. So
And
I'll do one
one more
more
thing, sir.
problem. Yeah, yeah.
Yeah. Uh, Before finding these roots, can we say that the system is marginal and unstable?
We cannot say that.
We cannot say. We have to find the
Yes.
roots, right? If it
No,
is
no.
in j
Sorry, sorry.
omega, hmm, my my question is,
Uh,
can we say before finding the roots of this auxiliary equation, can we say that the system has marginally stable?
no, we cannot say.
We
Only
have to
thing is
find the
that,
roots.
yeah, yeah. Only thing is that after first we are getting uh, these zeros case,
This,
correct?
yeah, yeah,
So then we are finding the auxiliary polynomial, its derivative, replacing with these numbers, and then continuing the calculations. Once the table is ready, we will check the first column. If we find that there are no sign changes,
that
temporarily we will say that system is stable.
is stable.
Then we will find the roots of the auxiliary polynomial.
Then we can
Okay.
say,
Then we can say system is marginally stable or not.
okay.
Okay. That is how we'll decide. If there are any sign changes, directly we will say that system is unstable.
Sir, if we get complex root repeatedly,
Com-
same complex
Sorry.
same complex conjugate roots that is in on imaginary axis
Yeah. If
repeatedly,
you get that, if you
then
get
what?
them, no.
Yeah,
If you get them like, let's say, uh,
repeated roots that if we
no,
get
they will be repeated, obviously. The roots will be repeated, obviously. Okay. Because we have even powers here.
no,
Okay.
sir. Yeah,
Uh,
here the roots, two roots are plus minus j1 and plus minus j25. If
yes.
four roots are same on imaginary axis, if we get plus minus j1 two times, then what will be? It will be
Still, they are
that
on
will
the
be
j omega axis
imaginary.
only, no?
Yeah,
Yeah. So if the poles are on the j omega axis, okay.
yeah.
So even only these the four poles only for this one. Okay. The rest of the poles will be on the left hand side only. Okay. So only the indication is that there are no poles on the right hand side because
Or if
this
the
has
roots lie in
decided
the
already.
right hand side, then
Sorry.
if the roots lie in the
No, that will
right
be
hand side,
decided
then
here itself.
okay,
Yeah, yeah. That negative sign changes will be decided. We
okay,
don't need to go and check here again.
okay. Understand, sir. Thank you.
Yeah, yeah. So these are the two cases. Next, I'll tell you one more example. Uh, that is important example. So let's say the characteristic polynomial is SQ plus 10 S square plus 31 S plus 30. Okay. Now, okay. We wanted to see, okay, how many poles, located in RHS of S is equal to -1 axis. Is the question clear? Okay, so previously we were discussing about, okay, this is sigma, this is j omega, correct? So here S is equal to minus j omega means what? S is equal to 0 minus j omega, correct? Yes or no? Okay,
Yes, sir.
that is nothing but what?
Yes, sir.
S is equal to 0 line, 0 axis. S is equal to 0 axis, j omega axis means real is 0, correct? Okay, S is equal to 0 axis. We are only checking the, yeah, till now, how many poles are there on the left side and right side of this axis only. Okay, now my question is, I'm taking S is equal to -1. What does this mean?
Shifted left
Yes,
side -1
yes.
axis.
So here we have -1. We wanted to see how many poles are on the left side of this line. using RH criteria. Okay, there is possibility that the
Sir,
poles may
you
be
have written
existed here
RHS.
also. RHS of this
Right
side.
hand side.
So right hand side. Till now we are checking only the RHS of J omega, because the regular RH criteria will give how many poles existing on the RHS of J omega. Okay. Now we wanted to check how many poles are there on the RHS of this axis. S is equal to -1. Okay. These kind of problems. So what we do is, so note, so to find, so number of roots on the RHS of some number S is equal to -a. Okay, so that will be like we take some Z, some other intermediate variable Z. So S plus A. Okay, then this means what is S? We are shifting it. S is nothing but Z minus A. Okay, S is nothing but Z minus A. So now we will check RH criteria in Z. Is this clear?
Oh, means we have to substitute the value of S as Z minus A in the original equation. Then
Yes,
we find the equation in terms of Z.
yes,
From
yes.
that,
So
we have to set the array,
yes, so we are
RHS.
transforming this. Let's say here in this example, S is equal to -1. So that means Z is equal to S plus 1. That means S is equal to Z minus 1. Okay. So now this polynomial, what we write, D of Z. Okay. Wherever there is S, substitute Z minus 1. Clear? Okay. So now if you simplify this, Z cube plus 7Z square plus 14Z plus 8 equal to 0. This is what you get. Okay. So now, so if you find it, let's say, let me write it here. Okay. So Z cube, Z square, Z and Z power 0. So what is it? 1, uh, 7, 14, 8. Correct? So what is this number here? 7 multiplied 14 minus 8.
19 by 7. 90 by
90 by 7. Okay. And this will be 0. This will be 8. Okay. Now you could see that there are no sign changes. Okay. Since there are no sign changes, okay, no sign changes. Okay. So what does it mean? No sign changes means no roots
no roots on the RHS.
on RHS of
S minus
Z is equal to
Z.
0. No, no. We are
Okay.
dealing with Z
Z
now.
is equal to
That means what? No roots on the RHS of S is equal to -1. Clear? So this is the transformation we did. Is this clear? Any query?
no, sir.
Any query? So I'm hoping that you understand the basic of this RH criteria. Okay. Next in root locus also we'll try to use this. So to see how the uh, roots are going forward. Okay. Now can you take this surprise test? Take the same example. Take the same example.
Like D of S.
Yeah, D of S is same. Okay. D of S is same. Okay. And uh, Tell me how many poles are there on S is equal to minus 2.5 axis. Same example. How many poles are there on RHS side of? So number of roots RHS side of S is equal to minus 2.5 axis. Okay, you have 10 minutes